Okay, so last lecture we looked at the supply of an industry, and now I want to look at equilibrium between supply and demand. So I'm going to start by talking about the existence of equilibrium, the correspondence principle, income effects, and incidence. These are sort of more the theory. So I'll start by discussing how the fact that we usually only think of there being a competitive equilibrium when there are a large number of people ensures the existence of equilibrium. And then I'll use the correspondence principle to link together the notions of comparative statics, uniqueness, and stability. I'll then talk about income effects and why for many of the problems we talk about, they don't really matter very much. And that will imply that equilibrium is often very similar to individual maximization. And we'll use this principle to establish ideas about tax incidence. And the reason why we'll think about tax incidence is that, as we'll discuss a little bit, it's very closely related to many other problems in economics. We'll then sort of apply these ideas to models of international trade, and we'll talk about three different models of international trade. The first is the Heckscher-Ohlin model of pure trade, and we'll use that to think about the Stolper-Samuelson theorem about who gains and loses from trade. We'll then talk about the Smith-Krugman-Melitz model of the division of labor, and we'll apply that to think about what are called home market effects and agglomeration. And then finally, we'll talk about the Ricardo model as formalized by Eden and Kortum, model of comparative advantage, and we'll look at how well that does at explaining the international trade in agriculture using a paper by Costino and Donaldson. Okay. The standard model of competitive equilibrium, which you guys probably learned either in intermediate or introductory graduate courses, assumes that everything is very convex, right? It assumes, and everything is very smooth. So people can buy perfectly divisible units of commodities, everyone has convex preferences, everything is sort of very nice, right? What I want to talk about now is what problems or not having discontinuities or non-convexities cause. Now that might sound like a really technical and sort of uninteresting problem, but if you think about it, most things that we buy in life are pretty lumpy. So like houses. If it were really the case that we needed all this smoothness, you would never get an equilibrium in the market for houses, right? Everyone only buys like one house or zero houses, right? Cars are similar. Or markets for spectrum, when the government auctions off spectrum, those come in discrete lumps that are very large, right? So in principle, our theory is not really going to say anything about these types of markets, right? And let me try to give you an example of the problem that in principle these sorts of lumpiness could cause for the existence of markets. So imagine that there are two people and two goods. So Charlie views the two goods as perfect complements and values each at $1. Sonia has either or preferences. So she wants one good or the other, but she doesn't get any additional value from getting both of the goods, right? And she values getting at least one good at 75 cents. Does anyone know Sonia Jaffe? Yeah, so she's the Sonia that this was named for. And you probably don't know the Charlie. Or do you know Charlie Nathanson, who visited here last year and took the price theory course with you guys? He's the Charlie this was named for.
What's the good then?
I don't know. It's just what we wanted, someone who began with C for complements and someone who began with S for substitutes. Okay, so can anyone explain, or Nelson is not in this class anymore. Can anyone explain why there's no equilibrium in this situation? Did anyone read the paper that explained? why there is no equilibrium in this situation. So, James, do you have a thought? Yeah. Yeah, Eric.
Well, so we want Charlie to end up with the goods, right?
Because any equilibrium has to be efficient, right?
Yeah. But since the sum of the two prices for the goods has to be less than one has to be less than 75 cents. So
Exactly.
Sonia will buy
At least one of the goods, and then Charlie won't get it. Or at least there will be excess demand. Yeah, that's exactly right.
But when you say values at $1, does that mean Charlie values them together? At
Yes,
$1?
values the pair at $1.
But Sonia doesn't want both for $1.50. She only wants one.
She only cares about getting one.
Oh, okay.
So she doesn't have any additional value for getting the other one.
Oh.
Okay, yeah. So the only the only efficient outcome would be for Charlie to have both. That's not an equilibrium. And one thing you could say is that the problem here, which is the way that you would usually set it up. Usually these models assume that there's a finite number of people and they have smooth preferences, right? And so a natural reaction is the problem here is that there's discreteness. So I think that's exactly the wrong way to think about it. I think the problem here is that you have only two people and that there's no problem with things being discrete. So let me try to explain why that's the case. So think about what would happen if Charlie started with both of the goods. Well, Charlie's not going to sell those goods to Sonia because the only time he'd be willing to sell them is if he could sell both of them. And Sonia's not going to take both of them, right? Off him for a price that's more than it's worth. If Sonia had one of the goods, she would sell it to Charlie for $1. And Charlie wouldn't sell the other good, right? So in the case when we actually had two people, there would be no problem. These guys would reach some bargain somewhere in between, and everything would be fine. And when there's a large number of people, I'm going to show you that there's no problem either. So the real problem was trying to apply a model, perfect competition, which is intended for a situation where there's a huge number of people, to a situation where there's only two people. You should really apply a monopoly model in the case when there's two people, right? Okay, so suppose now that there's a mass 0.5 of people like Charlie and a mass 0.5 of people like Sonia, right? Then, Chrissy, can you tell me what the equilibrium would be in that case? So imagine there's 0.5 people like Sonia, 0.5 of people like Charlie, and 0.5 of each of the two goods, which is basically the same as the problem we just talked about, except where there's lots of people. What would be the prices and what would be the equilibrium? Yeah, well, or if you read the paper, but I guess you didn't. Don't look at the slides. Can you figure it out? Think it through? Does anyone else want to try? Mike?
Like, someone would be satisfied as Charlie to get both goods, and then someone would also get one of the one good to satisfy part of Sonia's, and then the others would get one of the other good to satisfy the others.
And what would the prices be? Well, to get Sonia's to do both things, what do you need to have be the case?
It'd be under 75 cents for either one.
Well, they both have to have the same price, right?
Yeah, I guess.
Because otherwise Sonia's not going to be indifferent
150
between the two
cents.
goods. And the sum of the two prices is going to have to be 1, because otherwise Charlie's are not going to be indifferent, right? So you need to get both of those guys to be indifferent, so it's got to have to be 50 cents for each of the two goods, right? So the equilibrium is that half of the Sonias are satisfied with each good. That leaves 0.25 of each good remaining, right? And that's enough to satisfy half of the Charlies, right? So the reason why that makes sense is that on average, the Sonias sort of value each good more than the Charlies do. Because they value each good at 75 cents, whereas sort of on average in some sense, Charlie's only value the goods at 50 cents, right? And so you want to satisfy as many Sonias as possible and then move on to the Charlies, right? The prices are 50 cents for each good, and that leaves everyone indifferent, right? The question is, why doesn't 0.5 constitute an equilibrium in the finite economy? Vershank's not here, right? Does anyone else want to explain that? Why doesn't 0.5 clear the market in the finite economy? Well, the problem is that at those prices, Sonia would be happy to take one of one good, one of the other, and Charlie would be happy to take both or none. And so that gives us aggregate demand vectors that are 1, 0, 0, 1, 2, 1, or 1, 2. But none of those is exactly equal to 1, 1, which is what we have, right? So aggregate demand surrounds the aggregate supply, but is never equal to the aggregate supply, right? The problem is that you've got aggregate supply that's in the convex hull of the aggregate demand, but is never actually equal to the aggregate demand. You guys can turn in your problem sets up here. And the more people you have starts to convexify the aggregate demand, right? Because imagine we have 4 people. Well, now, rather than just having these points here, we can have people be sort of slightly closer in towards the thing. And in fact, that would clear the market. If you had 5 people, it wouldn't exactly clear the market, but you could get pretty close. And the more people you get, the closer you get to fully clearing the demand. And this basic idea works in any large finite economy. So if you have an even number, things work out perfectly. If you have an odd number, they're working out increasingly close. They fail to clear only by a single good as things get larger. Yeah, Neil.
Sorry, this is a stupid question, but
Yeah.
in the example, why would the other half of Sonia's pair up and give each Charlie up to $1.50? Because, like, I mean, like, each Charlie would rather have $1.50 than have the 2 goods, right?
Yeah, and that's exactly what happens when there is more than one Sonia. The problem is, it's in this silly world where there's only one Sonia, and when you have 3 Sonias, the problem is that every pair of Sonias pairs up, but then there's one Sonia left over, and she doesn't know what to do.
But in our competitive, tons of people example, why wouldn't the other half?
Well, that's exactly what happens in the market equilibrium, right? Effectively, all the Sonias get satisfied with one or the other goods. So you can think that every Sonia forms a pair and buys the goods from Charlie until all the Sonias are satisfied. And then the remaining goods are allocated to some half of the Charlies.
Oh, sorry, yeah. Okay.
Yeah. Okay. So I think that what you can think of is that when the prices are 0.5, then we should think that the outcome will be the efficient allocation and an approximate equilibrium. The fundamental problem is that we were trying to apply a notion of Walrasian equilibrium that only makes sense when there's a large number of people to a case when there's a finite number of people. When there's a finite number of people, either you need to think that there's an approximate equilibrium, because no one's going to act perfectly competitively, or you need to explicitly model some sort of oligopoly situation. So I think the broader lesson that you take from this is that A, large numbers fix a lot of problems. And in many situations, we're talking about cases with large numbers of people. Otherwise, we wouldn't be thinking about applying these sorts of concepts. And when you're thinking about large number of people, given that that makes your life easier, put it into the model, right? It's crazy if you're motivated to think about competitive equilibrium by the fact that there's a large number of people, and yet you write down a model with a discrete number of people, and that causes you problems. That's sort of